Welcome. So today we're going to put on our detective hats and investigate one of the most fundamental ideas in all of calculus, what it really means for a line to be unbroken and the powerful tool we use to prove it.
Okay, let's just dive right in with a simple question. If you can draw a function's graph in one single smooth motion without ever lifting your pen from the paper, then you've basically got the core idea of continuity down. But what happens when you can't do that?
Think about it like this. The height of a flower as it grows, that's continuous. It has to pass through every single possible height on its way up. But your bank account, that's discontinuous. Your balance doesn't flow smoothly from $1 amount to the next. It just jumps the second you make a deposit or withdrawal.
So that whole pen lifting idea is a great starting point, right? But in math, we need to be a little more precise. Our real detective work begins when we find graphs with these weird breaks, mysterious holes, and sudden jumps. This is the scene of our crime.
And the official term for these crime scenes, these breaks in the line, we call them a discontinuity. It's basically any point where that smooth, unbroken flow just fails. So let's start gathering some clues about how these breaks actually happen.
Our first piece of evidence is probably the most obvious kind of break you'll see, a sudden jump. A classic example of this is something called the Heaviside step function. It's just 0 for all the negative numbers, and then bam, it instantly jumps to 1 at 0. It's kind of like flipping a light switch. And this right here, this graph shows you exactly what I'm talking about. See, as you come in from the left side, following that blue line, the function is heading toward one value. But if you come in from the right on the red line, it's heading toward a completely different spot. The two sides just don't meet up. Okay, so our next clue is way more dramatic. Sometimes a function doesn't just jump. It completely flies off the charts, shooting straight up to positive infinity or plummeting down to negative infinity. We call this a vertical asymptote.
You see this kind of thing happen a lot when you've got a fraction, and the bottom part, the denominator, hits 0, but the top part doesn't. You're trying to divide by nothing, and boom, the function's value just explodes, heading for infinity. There is no way you're drawing that curve without lifting your pen. All right, now for the main event, our toughest case yet, the function sine of 1 over x. As you get closer and closer to 0, this thing starts bouncing back and forth faster and faster. It's completely out of control. It doesn't jump, it doesn't fly off to infinity, it just goes absolutely bonkers. So how in the world do we describe what's happening here? So, to crack these cases, we're going to need a special tool. A concept that lets us investigate what's happening right at the scene of the crime without ever having to actually stand on it. And that tool, our lead detective, is called the limit.
You know, the whole idea behind limits really comes from a pretty simple observation. Any smooth curve, if you zoom in on it enough, and I mean really zoom in, it starts to look just like a straight line. The limit is the mathematical tool that lets us do that zooming in.
Okay, let me walk you through this. Imagine you draw a line that connects two different points on a curve. That's called a secant line. Now watch what happens as you start sliding one of those points along the curve, getting it closer and closer and closer to the other one. The secant line starts to pivot, right? And it gets closer and closer to becoming the tangent line. That's the line that just barely skims the curve at a single point. The limit is what tells us the slope of that tangent line, right at that exact instant where the 2 points basically merge into one. And this brings us to a really, really important point. A limit isn't about what the function's value is at a certain spot. It's about what value the function is approaching as you get infinitely close to that spot from both sides. It's all about the destination, not necessarily the arrival itself. So now that we've got our lead detective, the limit, on the case, we can lay down the 3 official rules for continuity. First, the limit has to exist. The function has to be heading to the same place from both the left and the right. Second, the function actually has to have a value defined at that exact point. And third, this is the most important one, those 2 things have to be the exact same. The destination has to match the arrival.
All right, it's time. We are ready to tackle our toughest case, that crazy, infinitely oscillating function that just seemed impossible to pin down. For this, we're going to need a special technique, a really clever trap called the squeeze theorem.
So, let's just take a step back and look at the problem again. This function, sine of 1 over x, never actually settles on a single value as it gets close to 0. It just keeps bouncing between -1 and 1, forever. So how on earth can it have a limit?
The secret
It's a really clever technique called the squeeze theorem, and it's the perfect tool for trapping a function that just won't behave.
The idea is actually pretty simple when you think about it. Imagine our wild function is literally trapped between two other, much nicer functions. Now, if those two outer functions are both heading towards the exact same point, like two walls closing in, then the function that's squeezed in the middle has no choice. It has nowhere else to go. It has to approach that same point too.
Let's actually see this in action. Our wild function is now being squeezed by those two parabolas, right? The bounding curves. We know for a fact that both of those parabolas go to 0 as x gets closer to 0. And since our crazy function is trapped between them, it gets squeezed down and its limit has to be 0 too. Case closed.
So we did it. We solved our detective story. But, this isn't just about solving some math puzzle. Understanding limits and continuity is absolutely foundational to everything that comes next in calculus.
When you get right down to it, the entire field of calculus is built on this one powerful idea of getting infinitely close. Limits are what give us derivatives, which let us find the exact rate of change at a single instant. That's crucial for everything from physics to finance. And they also give us integrals, which let us find the total area of complex shapes by adding up an infinite number of tiny little pieces.
So, we started this journey trying to solve the mystery of an unbroken line. And we found out that this incredible idea of a limit lets us zoom in and find the slope at one single point. But this powerful idea has another equally amazing application. What happens when we use that same concept of getting infinitely close, not just to zoom in, but to add up an infinite number of tiny things? Well, that's a story for another time.